So the talk that I'm going to give today is it started with my PhD. It was carried on in my work at Pribana. It's now, some of this is now being applied at Unbible. And it's a joint work with a large group of people. I hope not to be forgetting someone. It belongs to this field in machine learning called structure prediction. That I think Xavier Carreras and Slav talked about today and yesterday, which is a machine learning framework that aims to do predictions with output variables that are highly structured, constrained, and interdependent. And by now, I think it shouldn't be hard to convince you that in NLP, there are many tasks that have to deal with this kind of structured and ambiguous textual data. For example, in machine translation, you need to translate from a sentence in one language to a sentence in another language. In speech recognition, you need to map an acoustic signal to text. In parsing applications, you need to map from a sentence to some tree representation or graph representation, and so on. So in all these problems, you need to deal with output variables that have a very structured form. So here's an example of a phrase structure parse tree, or also called the constituent tree. So I think that Slav talked about this a little bit in the morning. So basically, there's a grammar with some production rules. We have a sentence, and the goal is to basically use the grammar to build the parse tree for this sentence. And the parse tree here encodes the syntactic structure of the sentence. So there's been a lot of work in statistical natural language processing towards this problem. Another grammar formalism that has been used quite a lot is dependency parsing. So here, the input is also a sentence, but the syntactic representation is a little bit different. We don't have these phrases, we don't have these internal nodes in the tree. What we have is links connecting words directly. So here logic is the subject of place, role is the object, minimal is an adjective modifying role, and so on. So I think that some of you have been playing a little bit with these in these afternoon's labs. And there's also a long line of work on dependency parsing. So this talk today, I'm going to start by talking about turbo parsers that I'm going to define in a while. And in the second part, I'm going to tell you about a recent ACL paper where we kind of proposed a reduction technique so that you could do constituent parsing by just using a dependency parser as a black box. So let's start with turbo parsing. So first we need to define it. This definition that I'm providing here might sound a little bit enigmatic. I'm going to get into some details soon. So we're going to call it turbo parser any parser that runs inference in factor graphs, ignoring global effects caused by the loops in that factor graph. And I'm going to tell you what this means in a while. This idea of coming up with a factor graph representation and then doing approximate inference ignoring loops is something that is very inspired in communication theory. There's some turbo decoders and low density parity check decoders that use kind of the same idea. So what we are going to do here is to apply this same idea to general structure prediction problems, and in particular to parsing. And it turns out that there is a lot of work in parsing, in dependency parsing, that can be regarded as instances of turbo parsers. For example, there is work from about 10 years ago using integer linear programming formulation for parsing. There's another ILP formulation that we proposed, which is more compact than the one of Riddle and Clark. There's also a parser based on belief propagation, which also uses this idea of defining a factor graph and then running an approximate decoder in that graph. And there's some work using dual decomposition as the inference technique by Ku et al. And by ourselves a little bit later using an algorithm called AD-cubed. So all these can be regarded as turbo parsers. And another distinction that we need to make is between projective and non-projective parsing. So I think that Slav touched on this topic in the morning. Basically, a projective tree is a tree in which all arcs are nested. And the non-projective tree is one in which you have arcs that can cross other arcs. So for example, this is a non-projective arc, and if there is at least one non-projective arc in the tree, then we say it's a non-projective tree. So why should we care about non-projective trees? Well, there are some languages that have a flexible word order, like Dutch, German, Czech, and so on, for which it's convenient to use a non-projective tree representation to model certain linguistic phenomena. And so the way we are going to do this is we're going to define a factor graph representation for the parsing problem that tries to put together, tries to compute a score for a parse tree that decomposes as a sum of scores for several substructures of this parse tree. And the simplest substructure that we're going to consider is a single arc. So we're going to have scores for every pair of words, any arc connecting a pair of words. It could be this one, but it could be, it's in general, it's a quadratic number of arcs connecting all possible pairs of words. So we're going to have scores for all of these, but we're also going to consider higher order scores that look at pairs of arcs. So in this example, consecutive siblings. Basically, a head word learned with two consecutive modifiers, less and in. We are going to have a score for this entire structure. And we are going beyond that. So with consecutive siblings, we could regard it as kind of a horizontal Markovization assumption, but we also do vertical Markovization assumption, which is basically considering scores for grandparents. So in this example, there's an arc going from learn to lessened, and another arc going from lessened to out. And we consider even more arbitrary siblings, not just consecutive. Add bigrams, which are basically two consecutive words and the parents of those words. Third order scores for grand siblings, for tree siblings, and so on. And so the idea here is to consider all possible substructures that we can form with these arcs or tuples of arcs, and to obtain a parse tree that maximizes the sum of all these substructures. And this is quite challenging. It's a well-known fact, I think that Slav also mentioned that today, that if you want to go beyond arc-factored models, meaning that if you want to use anything more than just arcs, then non-projective parsing becomes a NP-hard problem. So these days there are approaches that use transition-based parsers, for example, that decode left to right. But if you want to actually do a global optimization to compute the parse tree with the highest score, this problem is intractable. And so we really need to consider approximations to solve it. And a lot of people did it, considering some of these substructures, a subset of them, or all of them. So I'm going to focus in this talk on our later work that uses AD cubed to parse. The basic idea is that we're going to define as the underlying structure a factor graph. So this is something that we can use in general for structure prediction, not just for parsing. And the idea is that you take our input x, which in the case of parsing is the input sentence, and we're going to consider the sets of all possible candidate outputs for this sentence. In this case, all possible parse trees. So we're going to call that set y of x. And then we're going to define a function that we call a compatibility function that takes an input x, a sentence, and a possible parse tree for that sentence, and outputs a number. And our goal is to pick the parse tree that maximizes that score. And the reason why we have a subscript w here is because we use a model, and w is the parameter of our model. So the key assumption that we need to make to solve this problem is that this function, this compatibility function, has some decomposition into parts. And the reason that we need to assume this is that it's not feasible to enumerate all possible parse trees, because there's an exponential number of them, and pick the one with highest. We cannot just do this argmax in a naive way. So you need to assume some structure on this function, and a convenient way of doing that is to define a factor graph. And so this is an example of a factor graph. We are putting all the output variables here on the right. Let's assume for the sake of simplicity that all these output variables are binary. And we are going to have some factors connecting some of these variables. And these factors are basically going to make sure that they are going to put constraints on some groups of these output variables. So for example, they can take 2 individual arcs and 1 sibling part, and making sure that you can only have this sibling part if the 2 arcs involved in this substructure are also present in the parse tree. So you can regard these factors as constraints and these as indicator variables for each of our substructures. Factor graphs are very general. We can regard simpler structures like sequential models, like HMMs, CRFs, and so on, also as examples of graphical models of factor. So we can have a factor graph representation for them. The nice thing about some of them, HMMs, CRFs, probabilistic CFGs, is that we can use dynamic programming algorithms to obtain the best configuration for these structures. But in general, if you have a very complicated graph that mixes all these complicated substructures, in particular, if there are loops in the graph, then there's no way we can do inference in a polynomial time, except in very special cases. And so what we are going to do here, so I'm talking about factors just as a constraint connecting several variables, but without going into details, we can also generalize that by considering these factors as sort of a machine that does some local computation for us. And algorithmically, this means that we are going to kind of approximate a global solution to this problem by using local computation performed at the factors. This is the underlying idea of several dual decomposition algorithms, message passing algorithms, and one algorithm that I'm going to talk about here. So you're going to go from that picture to something like this. So I'm going to briefly mention the alternating directions dual decomposition, or AD-cubed algorithm. It's a general purpose algorithm. It can be used not just for parsing, but for many other problems. For example, problems that you encounter a lot in NLP and information retrieval. For example, besides problems with factor graph representations, we also can address problems that involve statements written in first-order logic, problems that have some kind of budget or knapsack constraints. This arise very frequently in, for example, summarization problems or other problems in information retrieval, where there is kind of a budget of information that we can provide to a user, and also problems that involve building a rich model by combining simpler ones, by combining several structured models. So AD-cubed can be used for addressing all these kinds of problems, and the high-level idea behind it is to decompose the original complex problem into local subproblems. These correspond to the factors in the factor graph. And these factors, in order to get an output that is globally consistent, these factors, we need to constrain them so that all these substructures agree with each other. And the way to achieve this consistency is to iterate between solving the local subproblems and then penalizing the disagreements by using Lagrange multipliers. So I'm not going into details, or I don't have any equation here describing the algorithm. This is kind of the high-level idea. If you're curious and if you want to know more details about this, there are some references in these slides that point to the papers. And so in particular, if we want to deal with first-order logic constraints or with knapsack constraints, budget constraints, in that case, the local subproblems that you need to solve at the scope of each factor, they correspond to Euclidean projections onto hard-constrained polytopes. So just to give a flavor, in a problem involving first-order logic statements, we can decompose these statements in small factors. So this is showing some of the factors that involve some logical operations. And then the subproblems that we need to do correspond to projections onto polytopes, which are depicted here. And so the crucial thing here is that all these Euclidean projections can be performed very efficiently. So they cost only linear time with respect to the number of variables that are connected to the factor. And therefore, each iteration of this dual decomposition algorithm is quite efficient. So we have used AD-cubed to several problems. Parsing is an example, but also frame semantics, broad coverage semantic parsing, summarization, coreference resolution, and it in general works for any combinatorial problem that we can frame by using logic constraints, knapsack constraints, or other things that for which we can easily compute the best configuration locally at each factor. So here are some pointers to the literature. There's a book chapter on this volume on advanced structure prediction where we explain this in more detail. There's also a JMLR paper where we have some experiments also in graphical models. And if you are interested in general on the topic of how do these message passing algorithms, belief propagation, dual decomposition, integer linear programming, how all these relates to each other, there's a tutorial that I gave to MNLP 2 years ago that kind of tries to put everything in the same scope. So okay, so let's go back to turbo parsing. So we basically, by using all those substructures that I showed you a few slides ago and running these on the largest non-projective data sets, basically German, Czech, Dutch, and one non-projective data set for English, we got well, what at the time was the state of the art. I'm not sure if it still is, probably not, because there's been a huge advance in the last couple of years in the accuracies of parsers with the advent of neural parsers. But we still get very good results in speeds that are fast enough for practical purposes. So I also want to point out that this is kind of orthogonal to neural networks. So we could easily include some nonlinearities to compute scores for all these substructures, and then keep the same decoders, still using AD cubed to come up with the best parse tree for each sentence. So these two things can be they can marry each other. We also use this for semantic parsing. So basically the idea is the same, except that we don't have a tree structure anymore. We have a DAG, and but we can do essentially the same thing. And we also got very good scores in the semi-eval shared task by doing this. So if you want to try this out in your favorite combinatorial optimization problem, there's a toolkit out there that is freely available. It's implemented in C++. There's also a Python wrapper that make it easier to use. There are several built-in factors, for example, all these logical factors that I mentioned before, the budget ones, and so on. It's also possible for you to implement your own factor. So if you are working in a very specialized problem for which your factor you can basically optimize it locally, meaning finding the best configuration only locally at that factor, you can write this function and put it together and use AD-cube to decode the entire factor graph. If you just care about parsing, the parser is also publicly available. It's also implemented in C++. There's also a Python wrapper. So these days, it's actually more than a parser. We have a full NLP pipeline. We use it at Unbabel. You can do part-of-speech tagging, dependency parsing, semantic role labeling, entity recognition, and so on. And all of those you can also train on new data sets. Okay, so this finishes the first part of the talk. So I'm going to move now to more recent work that was presented last year at ACL, where the idea is to basically, instead of implementing a constituent parser, just reuse a dependency parser. So there is this folklore idea that constituent parsers are inherently slow because they need to deal with this heavy grammar constant that makes the CKY algorithm slower than, for example, the Eisner's algorithm. And dependency parsers are typically regarded as faster, but their output is less informative because it doesn't give you the actual phrases. And for some downstream applications, you do care about the segments, the phrases that constituent parsing can provide. So how can we get the best of both worlds? Our proposal in this paper was to reduce constituent parsing to dependency parsing. And so it works for any out-of-the-box dependency parser. In this paper, we use turbo parser, but it could be any parser. It could be the new exciting Google parser that Slav told you about this morning, or any other that you prefer. The idea of this reduction is rooted in a new formalism that we call add-order dependency trees. And the nice thing is that this is a very simple way of getting a constituent parser for free. And it's also competitive to existing constituent parsers. So we got reasonable scores for English and good scores for morphological rich languages. And if you apply this to discontinuous parsing, I'm going to tell you what this is in a minute, then we actually surpass the state of the art. Okay, so let's revise what continuous and discontinuous constituent trees are. I think that in the morning Slav told you about continuous trees. These are basically parse trees that can be generated by context-free grammars. So the property of these trees is that the yield of each internal node is always a contiguous sequence of words. But there's also, for some languages, it's also useful to consider discontinuous trees where the yield of a node, for example, this NP here, can have gaps. So for example, this word is not in the yield of this NP. It belongs to another node. And so there is a gap here. And graphically, you can tell it because you have these two crossing edges. So to generate discontinuous trees, you need to go to mildly context-sensitive formalisms like linear context-free rewriting systems or others. But the problem with that is that the complexity of parsing algorithms for those formalisms, while still being polynomial, it has a very high degree. So it takes a lot of time to parse. And existing parsers are also not very accurate. So if we go to the dependency world instead of the constituent world, we also have these two kinds of dependency trees, projective and non-projective, which is kind of the same distinction that we have for continuous versus discontinuous constituent trees. So in fact, we can show something more rigorously about this. Like we can show that we can project continuous constituent trees to projective dependency trees and discontinuous constituent trees to non-projective dependency trees. And we have seen already that we like non-projective parsing because it's good for languages that have a flexible word order. So here's a kind of graphic explanation about how this projection works. So we start with a constituent tree, in this case a continuous one. We write down all the production rules that are involved in this derivation. And then we go to each production rule and we designate one of the children nodes as the head node. So for example, in this case, we say that if you have a sentence that is written as an NP, a noun phrase, and a verb phrase, the verb phrase should be the head node. And in an NP, the noun should be the head node, and so on and so forth. So if you do that, then we can mark the head nodes in the parse tree, and then we can propagate bottom up all the lexical, all the words to each node. So we can basically decorate each internal node with a word that comes bottom up. For example, here public is a noun, and this noun is the head of this NP, and so we just propagate public to this NP. We do the same here with the verb is, and then is becomes the head of the sentence because the verb phrase is the head of this production rule. So, and then the next step that we need to do is just to drop the constituent nodes. And if you do that, we end up with a dependency tree. So it's very simple. I think that Slav might have explained this also in his lecture. So the problem with this is that this is a one-way transformation. You cannot invert it. Basically, if we had started with the dependency tree, for example, if you start with this simple structure, this simple dependency structure, just a head word with two modifiers, there are several different constituent trees that you could obtain that would project into this dependency tree. For example, we could left branch, we could right branch, or we could have a flat structure. So these two modifiers could be in a flat structure. So we need to in order to provide a correspondence between constituent trees and dependency trees, we need to make these, we need to endow dependency trees with some additional structure. And this is what this paper is doing to provide formal equivalence results that allow to invert this projection. I have to mention that there's a lot of related work. There is work going back to 2008 by All and Niver, where they basically try to build a constituent parser by storing structural information about the constituent tree as the dependency labels. This is very similar to what we are trying to do. We're going to compare our approach with theirs. There's also work with a different motivation. So there are many annotation efforts to build good tree banks, and in particular multi-representational tree banks that includes constituent trees and the dependency trees. And to establish a correspondence between the two, people have come up with manual transformation rules. So this is kind of more with a linguistic motivation. There's also work that tries to do constituent parsing in two stages. In one stage, they do dependency parsing, and in the second stage, they do constituent parsing by constraining the constituents to be consistent with the dependency tree. And there is work in which the two things are done together using dual decomposition or more sophisticated grammar formalisms like spinal tree drawing grammars. Okay, so let's formalize add order dependency trees, and let's start with the simpler version, which is what we call strictly ordered dependency trees. So the key idea is extremely simple. We are just going to end out dependency trees with additional structure by encoding the order in which each add is attaching its modifier. So for example, if we start with a sentence like this, whose head is the verb is, let's say that is first attaching the modifier cautious, and we denote this by #1 to denote the fact that this is the first event. It's the attachment of cautious to is. And by doing that, we are going to form a VP. So we can look at the consistent tree and form a VP here. And the second event is going to be is attaching public as a modifier on the left. And by doing that, we form this S node. And this defines the complete constituent tree. So this is very simple. We just define the order in which these modifiers are picked. And we have this nice result that tells us that there is so the set of binary constituent trees, meaning trees that in which each internal node has two children, except the pre-terminal nodes. So the set of binary constituent trees is isomorphic to the set of strictly ordered dependency trees. And not just that, but this is done using the same number of symbols. So basically, all the symbols that exist in the dependency alphabet are the same as the symbols in the phrasal alphabet. Is there any questions so far?
How would you represent a tree with the same level of nodes in this as a dependency tree with ordered information?
You mean a tree which is not binary?
Right. Sorry. That was the question.
Okay, yeah, I'm going to talk about that in a while. So the question was, how can we represent multiple children? I think that was what you were asking. Yeah, so we are going to explain that in a while. But this result so far is restricted to binary trees, okay? So only trees that are, for example, in Chomsky normal form, where you have just like a node with two children. Any other question? Okay, so there's one way of regarding this isomorphism result that is very intuitive, which is to look at the spine of each word. So we can go back to the constituent tree and lexicalize it, basically designating head childs for each production rule, and then propagating the words bottom up in the tree. And we can look at in which position in the spine of each word each modifier is attached. Okay, so for example here there are these two words, H and M1, and the first thing that we are doing is to form a constituent Z1 that spans these two, and then we have another constituent node, Z2, that puts together M2 and Z1, and then we have another Z3 that puts together M3 and Z2. Okay, so if you do that, and if we keep track about what was the position in the spine where we attached each modifier, then we end up with a representation that is exactly our add-ordered dependency representation. So basically, these numbers encoding these events correspond to the positions in the spine where you are attaching the modifiers. So this is very intuitive. And let's now proceed to the case where we want something better than just binary constituent trees. To do that, we need to consider this more general class of weakly ordered dependency trees. And the definition is essentially the same as before, except that now we allow for simultaneous events. Okay? And the only constraint that we put is that the dependency label needs to be consistent. So let's look at an example. In this sentence, let's assume that the first event attaches simultaneously the word still and the word cautious to the verb is, and it's forming a constituent which is a VP. So in the constituent tree, this corresponds to creating a VP node here. And this is being marked as the first event that you have. And then you have the second event, which is basically creating a hash node, and then we have the full constituent tree. So this seems to be solving the problem, so we can ask the question about, can we represent every constituent tree by doing this trick? What do you think?
Unary will probably not. Like if you have unary rules in
Yeah.
the constitution.
Exactly. So basically, this is fine, except that unaries are lost. It's exactly what you said. So basically, if we have, for example, a unary node here, so a node, a verbal phrase that points to RB and an adjectival phrase that points to JJ, then these two are two unary nodes, and there is no way that we could encode these two nodes in this representation. At least no clean way of doing that. So by doing this, we are sacrificing these unaries. But we still have this proposition that if our constituent trees does not have any unaries, if it's unaryless, then this is isomorphic to the set of weakly ordered dependency trees. This is still a useful result. So the next question that we're going to ask is, can we use this framework to relate projective trees and continuous trees? So this is what we're going to do next, but we need to define another property, which is the nesting property. So here's the definition. So we say that the head ordered dependency tree has a nesting property if on each side of every head, the closer modifiers are attached first. So for these examples, this word satisfies this property, this sentence satisfies this property, but not this one. Because this event here, the attachment of this word still to is done after attaching cautious. So we are attaching a word that is further apart, cautious, before attaching one that is closer to the verb is. So this is violating this nesting property. And the result that we have then is if our tree is unaryless, our constituent tree is unaryless and continuous, so if there are no gaps, if there are no discontinuities in the constituent tree, then the class of such trees is isomorphic to the dependency trees that are projective, weakly ordered, and have the nesting property. So basically, to be continuous, you need to have these two things. The dependency tree needs to be projective, and it needs to satisfy this nesting property. So here's an illustration that shows us two violations of this, like a tree that is projective but not nested. So in this case, this dependency tree is projective, but this node 3 is being attached before node 2, so it's violating the nesting property. And the corresponding constituent tree has this discontinuity. So this node A has a gap here. The second example is the opposite. So this is a tree that satisfies the nesting property, but it's not projective. So there is one arc here that is non-projective, that crosses another arc. And this results also in a discontinuous constituent tree. So there is a gap here. Is this clear to everyone? Any questions at this point? Okay. Okay, so given these formal relationships, let's see how we can use this in a constructive manner to build a constituent parser. And so we just need to follow these steps. And some of them are pretty obvious. So the first step, we kind of have explained already how to do it. So we need to convert the constituency tree bank, a tree bank with constituent trees, to add ordered dependency trees. And this is done by just using this relation between these two classes of trees. You can immediately map one to the other, and by doing that, we are going to lose information about the unaries. The second step is to encode, somehow encode the head orders in the dependency labels. And this I'm going to talk about next. But after doing this, we are going to have a dependency tree bank, and we can just train a standard dependency parser, any dependency parser, in this tree bank, and then run it on new sentences. The step that we need to do after this is to convert the predicted dependency trees into constituent trees that don't have unaries, and then you need to recover the unary nodes. So the things that are missing here are these three steps, basically. And I'm going to talk about how to encode the add orders next. So we're going to consider three different encoding strategies. One that we call direct encoding, which basically just treats these numbers here as part of the dependency label. This is a very simple strategy. So in doing that, we are going to expand the number of dependency labels in our alphabet, but hopefully it's not going to be too bad. The second strategy is a little bit smarter. So we're not just encoding these numbers in a naive way. We are going to encode the differences with respect to the previous modifier. So basically this +1 and this 0 here is the delta, the difference between the previous modifier. And by doing that, we expect to save some of the dependency labels, to come up with a smaller vocabulary of labels. The third strategy that we're going to consider is the one proposed by Alan Never, where they essentially store the entire spine in the constituent tree as a dependency label. So this is a very rich representation. There's a lot of redundancy in these labels, but they provide very rich information. But on the other hand, they're going to result in a very large vocabulary for the dependency labels. And to see the impact of these different encoding schemes, we are evaluating them on the development set of the Pen tree bank, where we basically see how many labels, how many dependency labels we end up with by using these three techniques. And for this tree bank, what we can see is that we save a little bit by using this delta encoding technique. Even if you do direct encoding, it's not so bad. We get 75 labels. I don't remember how many labels we have without these extra annotations. I think it's about half of these. So we're kind of doubling the number of labels, but it's not too bad. But on the other hand, if you use the Alan Never technique, we end up with kind of 10 times more labels than the other strategies. And this is actually going to impact the final accuracies in a very bad way, because if you then train a dependency parser with such a big set of labels, it's going to be hard to generalize just because we need to have a classifier with a lot of labels, and some of them are very sparse. So this is going to lead to a loss in accuracy. We end up with kind of 1.5 points improvement by just using the delta encoding technique. There are more details about this in the paper. I'm just going to move to the other step, which is how to train a dependency parser on the tree bank. This raises the question of what dependency parser should we choose, and how the choice of dependency parser affects the final performance of the constituent parser. So here I'm comparing a transition-based parser, malt parser. This is basically the parser of Never and others. The minimum spanning tree parser of McDonald. These two are pretty old, so even if you look at the dependency accuracies, they are way below more recent parsers. I also compare with ZPAR, which is a more recent parser, shift-reduced parser, kind of similar to malt parser, but better. And different versions of turbo parser. I don't have numbers with some of the most recent parsers that didn't exist 1 year ago. They are probably better than the ones that we get with turbo parser, very likely to be better. And I'm also looking at the speeds of each of these parsers. So we can see that there is kind of a trade-off between how fast we want our constituent parser to be and what's the accuracy that we want. So we can get something that parses very fast, kind of 5,000 tokens per second, but the accuracy is quite low, or we can get something that parses about 1,000 tokens per second, which is not so bad, and gets F1 scores that are much better. So I'm going to compare later these scores with other constituent parsers to see how this can be compared with the actual constituent parsers that are developed from scratch and not using this reduction technique. Okay, so let's move to the final step, the recovery of the unary nodes. This is the only thing that this model cannot capture. But what I'm arguing here is that this is actually a very simple problem to solve. So we just recovered unaries by running an independent classifier at each constituent node. So basically we take our constituent tree without unary nodes, and at each internal node we are going to treat it as a classification problem in which we assign the null class if you keep the node as it is, or a class that encodes a unary spine if we want to add some unary nodes on top of it. So it's a very simple problem, and for the pen tree bank and other tree banks, in the majority of cases you don't need to do anything. There are not so many unary nodes. In some other tree banks it's different, but you can still use this technique to solve the problem. And also there is some simple techniques that we can use to speed up this search. So we can just consider for each internal node, for example for a node JJ, only the unary spines that were observed in the training set. We don't need to consider all possible spines that we could form. And if you do that, we realize that we can do this in a very fast way. So a tiny fraction of the time of the final parser is going to be spent in this step. This is just a post-processing step. And the Oracle scores are pretty high. So this is basically the score that we get if we provide to the parser the gold standard constituent parse tree without unaries, and we want to just recover those unaries. We get something that is almost 100%. So this is a very easy problem. And now we're going to look at some experiments by using the entire thing by evaluating the entire thing on the test partition of the pen tree bank and comparing with other parsers that were state-of-the-art last year. So I'm showing here, I'm graying out parsers that use some kind of ensemble system or re-ranking or use additional data, semi-supervised systems, and I'm focusing the comparison on parsers that are kind of a single parser. They're not a combination of parsers, and they're just using the information in the pen tree bank. So what we can see is that some of these parsers are quite old. The ones that are worthwhile to compare against are the Berkeley parser, which gets an accuracy, an F1 score of 90.1. We get something similar, kind of 5 or 6 times faster. There's also the shift to reduce parser of Zhu et al. That is slightly better than ours. It has a little bit better accuracies, and the speed is slightly better. There's one that has much better accuracy, the one of Carreras et al. It's the spinal tag formalism. But this parser is a lot slower. They don't report speeds, but the decoding algorithm is too expensive. So I'm pretty sure the speeds are several orders of magnitude below these ones. So it's not the best parser that we can use for English. There are others that are probably best choice, both in terms of speed and accuracy. But it's already something decent, given that we use this very simple approach of just reusing a black box dependency parser. So the thing is even better if you look at morphologically rich languages. So these are tree banks for languages that typically have a rich morphology, like Basque, French to some extent, German, Hebrew, Hungarian, and so on. So there is a shared task that evaluates different parsers on these data sets. And if you compare with the single system parsers that do not do ensemble, then we get the best scores for the majority of the languages, and the average score in the end is better than the Berkeley parser and the best single systems in this shared task. But the real benefit that we got, the best results that we got, are for discontinuous parsing, which is considered a difficult problem. So for this, we use the Tiger tree bank, which is a tree bank for German, and we compared our approach with previous approaches by Yannick Versley, who uses the EasyFirst parser, Alan Niver, which uses basically the approach that I was describing using their labeling and encoding technique, and a system by Van Cronenburg and Bod that tries to parse directly these discontinuous trees by having something similar to CKY, but for discontinuous parsing. And what you can see is that if you look at the F1 scores, there is you gain several points comparing with the current state of the art. And this reflects to the exact match score. So these are basically the percentage of the sentences whose full parse is correct. So we can move from, well, here it's not so striking, but if you look at this other partition, you get a very big jump in exact match scores, which can be useful for some downstream applications where it's important to get not just more words correct, but the entire sentence well parsed. And so one of the things that I want to point out is that some of these parsers in previous work, they are so slow that they need to constrain the length of the sentences in which these numbers are reported, which is bad. So in the paper we have also numbers for the full, all the sentences in the test set. But before our work and with a couple of exceptions, the existing parsers were too slow. And these are results on another discontinuous tree bank, the Negre tree bank, also for German, where we get similar gains. Just to give an idea about how long this takes, we parsed all sentences in the Negre corpus in 27 seconds. In a single score, this is about 600 tokens per second, which is orders of magnitude faster than the system of Van Cronenburg and Bod. The speed is similar to the easy first system of Versley, but our accuracy is much better than theirs. So this concludes the talk. So in this second part, we have proposed a reduction technique for quickly implementing a constituent parser if you are lazy and you just have a dependency parser around. This technique is very simple, it's very flexible. We can take out turbo parser and use your favorite parser, dependency parser, to accomplish the same. It will be very interesting to look at, for example, the new parser coming out from Google, which is very accurate, and see if we can get even better scores in constituent parser by parsing by doing that. If the dependency parser is non-projective, then you can predict discontinuous constituent trees. And I think this is actually the most interesting contribution of this paper, because it actually made a difference in discontinuous parsing in terms of accuracy. We have showed empirically that we got some highly competitive constituent parsers for English and morphologically rich languages, but most of the benefit came in discontinuous parsing of German. So this is it. So in this talk, I didn't talk much about the current work that we are doing at Unbible, but I want to point out that we are hiring. So if you like machine translation, if you're excited about crowdsourcing, if you have been enjoying Lisbon so far, if you like the lifestyle that we have here, then you might consider to apply. We are also taking interns, so this is another thing that we might consider. The team uses to surf every 2 weeks. So if you like surf, it's yet another thing. And there are a few people from Unbible seated here, so I think 4 of us, counting with the steering committee, the organization, and the monitors. One of the founders is actually seated right here, so feel free to approach us if you're interested. And that is it. Thank you for listening, and I'll be happy to take questions.
Thank you, Andre, for keeping up so well with time. So, are there any questions? There's a question here.
So thanks for a great talk, Andre. So the third point here, or actually you said that we can use black box dependency parser to create a constituency parser for a language where we don't have a constituency parser. But I didn't understand how we can get those labels. So our labels like NP, number 1, or these kind of labels for the edges in the dependency parser if we didn't learn them from a tree bank or something.
Oh, no, so sorry, I was not clear. So I was assuming that there is a tree bank available. So I assume that you have a constituency tree bank for that language. And we just don't want to implement a constituency parser from scratch.
Okay.
You can just reuse any dependency parser that you have available, plug it here, and automatically you'll get a constituent parser. But we need a tree bank, yes.
Okay, thank you.
Any other questions? So there's one back there.
There's one there.
You can start.
In the 83 algorithm, can you give examples on what it means for the subproblems to overlap or to be globally consistent, and how does that translate to the Lagrange multipliers, please?
I missed
To the Lagrange multipliers.
Okay. So yeah, that part I kind of went a little bit fast. But suppose, for example, for parsing, one of the substructures that you might want to use, let's say it's a grandparent structure. So you have one arc going from one word to the other, and then another arc going from the second to a third word. But you can only say that that substructure is present in the dependency tree if the two individual arcs are also present, right? So if you create, let's say, 3 binary variables, one for the 2 arcs and another one for the grandparent structure, we need to constrain that if the grandparent structure is active, if it belongs to the tree, so do the 2 individual arcs. So this is going to be a constraint, okay? And the same kind of constraint holds for the more complicated substructures. This is one of the simplest examples, but we can also, I didn't talk much about that, but we can also use AD-cubed when you have kind of a larger model of the problem. Like, for example, you can also compose an entire sequence model with, let's say, PCFG, as long as you have an algorithm that allows you to compute the best tree from the PCFG and the best sequence from the sequence model, you can put the two together. And the constraint will be that whatever you are encoding in the sequence and whatever you are encoding with the PCFG must match. I don't know if this answers your question, but... oh, and you asked also about the Lagrange multipliers, right? So the Lagrange multipliers are penalizing the differences between kind of the different... so the variables that are repeated, like, okay. Let me go back to the example where you have 2 arcs and 1 grandparent. Let's suppose that you have other grandparent structures, including the same arc, one of the arcs. Okay, so this arc is going to belong to, let's say, 5 different grandparent structures. Okay, so each of these grandparent structures is giving you is telling you something about whether that arc belongs to the tree or not. So this kind of, you have 5 views of the same variable. So with these 5 views, you can average them and have a number. And the difference between the average and each of the individual views correspond to the Lagrange multiplier. And the Lagrange multiplier behaves kind of a message that is being exchanged in the scope of the algorithm. So it's like message passing where the Lagrange multipliers are kind of messages.
Any other questions? So no. So thank you, Andre, again.